Magnetic force on a moving charge. An electron travels horizontally at a constant speed of 8.6 times 10 to the 6 meters per second and enters a uniform magnetic field that is directed into the page. Now be careful. Our right-hand rule deals with positive charges, but now we have a negative charge. So on the diagram, show the direction of the magnetic force on the electron as it enters the field, show the approximate path of the electron, then calculate the magnetic force on the electron, then the acceleration of the electron, and calculate the radius of the path that the electron follows in the magnetic field. We're going to use the right-hand rule, so point the four fingers of your right hand in the direction of the velocity. And the electron's going this way. Your fingers will curl perpendicular to point in the direction of the magnetic field, which is into the page. Or please note that that's the direction your palm is facing anyway. And then your thumb will point in the direction of the force on a positive moving charge, which is up. So the force on a positive charge is up. But since we have a negative charge, you have to flip it around. So the force on the negative charge is down. So the answer, the force points down. Show the approximate path of the electron. The direction of the magnetic force will always be perpendicular to the direction of the velocity. So the electron will travel in uniform circular motion, hopefully you remember that from mechanics, while it is in the magnetic field. The initial force is down, so here the electron was coming in like this. It felt the perpendicular force, so it's going to go like this in a circle, which is clockwise. So it's curving downward inside the field. Calculate the magnitude of the magnetic force on the electron. Well, that is QVB, right? When you had a wire, it was ILB, filb, but this is for a charge. You put in the charge of the electron. If you don't remember it, this should be on your table of constants. But you know, you use it long enough, and this is one of those fundamental constants of the universe that's pretty important. So it's 1.6 times 10 to the minus 19th coulombs. You multiply that by the speed, which is 8.6 times 10 to the 6. Multiply it by the magnetic field, the applied magnetic field here, and you get a force of 6.19 times 10 to the minus 13 newtons. Calculate the acceleration of the electron. We never do get away from dynamics, or kinematics for that fact. We have Newton's second law, F equals ma, and that works for any force. This time we have a magnetic force. Divide both sides by m, and we have the acceleration is a magnetic force, which we have found, by the mass on the electron. So you can either remember that if you use it enough, or that will be on your table of constants. And if you don't want to memorize it, you don't have to. Or most teachers should let you get it off the table, I hope, or many teachers. So you find the acceleration is 6.79 times 10 to the 17th meters per second squared. Calculate the radius of the path that the electron follows in the magnetic field. Now remember, we said it moves in a circular path when it's inside the magnetic field, and it's a circle, it'll have a radius. Since it moves in a circle, we use the equation for centripetal acceleration. We do not have linear acceleration. So A is equal to v squared over r, and we're solving for r, so r is equal to v squared over a. Basically, you just switch those. That's not the precise mathematical way of saying it, but it works. So we square our velocity of the electron. Make sure you pay attention to that. Divide it by the acceleration that we found, and you get 1.09 times 10 to the minus 4 meters.